Can you hear me?
Yes.
This is Sweeper.
Hey.
I'll do my intro. Every time, every week when my is like starting from scratch, I'm on my phone because I've been coding for 25 years, 30 maybe. Um, I'm laid off, making sure that I'm active and learning new things while I look for a job. And this looks like a great group. I was with it in its previous life, and happy to jump back into this book that's pretty meaty. It looks, and it's a good thing to be doing with people, I think. So excited to get back on this project.
Yeah. Welcome back. Anyone else have any questions?
Yeah, I don't have the book yet, but it says clean up the book tonight. You have the requirements set up the library.
It depends on the project that we're working through. So as we move through the project, we'll encounter like the libraries that we need, and yeah. So you'll see as we work through the code. Like I'm gonna take little detours to actually set up small libraries and that sort of thing. But this project, I believe, is only Scikit-Learn. Like it's Scikit-Learn, and then the typical Python libraries like pandas and NumPy and that sort of stuff. But I'm new to Python. Most of my experiences with JavaScript, so I'm going to be figuring stuff out as we go along too. But it shouldn't be too bad.
Is there a PDF we shall be referencing or something? Or you can share your screen right
I'm going to share my screen. Yeah. Yep. And then yeah, if you want to grab the book just so you could work through it during the week or on your own time, that's totally fine as well. Like during the week, I'm working through the book just on my own, so I'm moving at a little faster pace. I'm on chapter 3, just going through the classification stuff right now. This is the first end to end. Let me go ahead and share my screen so you could all see what I'm talking about though. There we go. All right, what other questions do we have before we get started? Yes, chapter 1. Well, last week we started at, chapter 2. Chapter 2 is the first real project. In the event description, I said just try to read chapter 1 before you come to the event. It's going to make it a lot easier just to talk and understand what we're doing. Chapter 2 is the end-to-end machine learning project. So this is where we're actually building a real project. And yeah, last week we started the beginning of chapter 2. We worked through basically all this stuff, the big picture, framing the problem. What are these called? The cost functions. And now we just got to the part where it's get the data. So for those who want to work through the Google Colab and don't want to do the actual coding themselves, or they don't have a code editor to do it themselves, I'll go ahead and post this link right here. This is the Google Colab, I believe. This will lead you to the Google Colab. It will display the list of Jupyter notebooks for this book. Yeah, okay. So let me go ahead and, if you look, we're all in the machine learning channel. So if you go to the right, you're going to see an open chat, a create, invite, and an edit channel. Click on open chat, and I'll go ahead and post the Google Colab right there. So if you pop in here, you'll see the Google Colab pop up, and then you'll see the Jupyter notebook here. So end-to-end machine learning project. If you want to go ahead and actually run the code as we go through the book. I'm going to be typing out the code personally. I like getting the muscle memory, and just I feel like I learn better that way. So we could either have someone continue reading while I'm typing stuff out, or discuss what's going on in the code, that sort of thing. So, but like I said, we're gonna move slower. And for those who are like, well, this is, I kind of just want to move a little bit faster, we have go to choose a specialization channel. Inside the choose a specialization channel, you can see the brain here is machine learning. So if you click that brain, it'll unlock a channel called machine learning down here in specializations. And then that'll allow you to keep the conversation going during the week if you're working through the book on your own, or if you just want to talk about new stuff in the news or whatever. It's just a channel for continuing the conversation during the week when we're not partaking in the event. All right. So if no one has any other questions, we'll just start working through the book, and feel free to just shout out and ask questions as we go along. Yeah. So this is all information about the Google Collab. So in typical environments, your data would be available in a relational database or some other common data store and spread across multiple tables, documents, files. To access it, you would first need to get your credentials and access authorizations and familiarize yourself with the data scheme. In this project, however, things are much simpler. You'll just download a single compressed file, housing TGZ, which contains a comma separated values, a CSV file called housing CSV with all the data that we need for this project. Rather than manually... What?
Oh, sorry. I didn't know.
Yeah, I can hear you. You had a question?
The link to the book.
Oh, it's just O'Reilly. I'm using O'Reilly.com. I don't have like any PDFs or anything like that. I found PDFs from the previous version, but I didn't find any free versions of this book. Feel free to follow along with me on my screen, or I'm using O'Reilly, so O'Reilly.com. They do a free 10-day trial if you want to just try it out and see if you like it. Otherwise, I believe most people are ordering the book from Amazon. Yep, for sure. So rather than manually downloading and decompressing the data, it's usually preferable to write a function that does it for you. Obviously, we don't want to have to manually do it every single time. This is useful in particular if the data changes regularly, which I'm sure it does. You can write a small script that uses the function to fetch the latest data, or you can set up a scheduled job to do that automatically at regular intervals. Automating the process of fetching the data is also useful if you need to install the data set on multiple machines. So this is the function here. I'm going to go ahead add these libraries to my code editor. If you're looking at this in the Jupyter Notebook, feel free to run the code and comment on what you're seeing. Feel free to ask questions. And I'm going to be typing this code, so don't expect me to answer all the questions or comment on everybody who's working through the Jupyter Notebooks. Feel free to just chat among each other, okay? And then we'll move on.
So is that just an empty project you have?
Yeah, this is just an empty project. Yeah, I'm using PyCharm for mine, so I just like to get the, you know, get the hands-on experience and actually type things out, especially when I'm brand new to something, so it really sticks. But feel free to do it however you want. I posted the Jupyter Notebook in the chat, so feel free to just like run the code that we're working through, and feel free to comment on it. So what do you guys all think about this here now that you're running the code?
So I'll just note in passing that you sort of touched on different versions of data, and in real life that's absolutely an important concern. That one of the good things about writing code which compacts data, creates rows from a changing database, is that you can set up that code to freeze the data, or at least modify your code and row from that table So the summary is keeping track of code versions matters and Git commits. Track data versions also helps.
If I were to add a comment, it would probably be that if I was writing this function from scratch, that I would make the URLs or things like that parameters. So that's more reusable, right? As a kind of just having your part code. Yeah.
Mm-hmm. Mm-hmm. Has anybody run it in the Jupyter notebook yet?
It's very convenient for default URL.
Say that again?
The remark about parameterizing the URL makes sense in a great many languages. Very nice about Python is in the function signature, you can specify a keyword default say URL equals, and that's often a good way to sort of very manifest concept. Just put a signature, then in principle you could change it like you hit a task with all this function with the smaller data sets and anything that's passed. But it gives the reader a pretty good idea of which perhaps are foul and we're anticipating to be wrong.
I put a link to the third edition in chat.
Just a reminder to everyone to be careful with PDFs and free versions shared over the internet, obviously. Alright, so this function is, yeah, so basically what we're doing here, I guess you have to do 2 spaces in between, that's what Python likes. So we're basically making a request here, right? This is going to be our path. And then we're checking to see if the path is a file. If it's not a file, we're going to run this here. This is the URL we're reaching out to actually collect the data. We're going to be creating a directory called datasets. That's where our data is going to be stored. URL request. We're going to be making the request here for the data. And then, all right, so let me go ahead and load housing data. Housing, let me go ahead and
install the pandas library.
oh yes, yes. That's gonna be in settings.
Is your Python linked to your virtual environment? Like is the one in your terminal? Right, if you say source.ven /
Possibly. I was doing it manually.
I mean, like, just type like the Python -m install pip -m pip install library.
Python. Hold on.
Python pip install.
Yeah, hold on.
It should work. Like, go in the terminal and
Let me see how I get the terminal.
you could open it.
view. I think it should be in the view. Go to view. Yeah, view and then
There we go. All right, what'd you say? Python.
Python space -m. Just check version first. -v. Just do -v first. Hyphen. Okay, yeah.
Yeah.
Control, yeah.
exit parentheses.
Yeah, exactly. It's very irritating. Like it, I don't know why it opens this.
Yeah.
Now the
Yeah, typically I was going to settings, and then I would just, I'd install it manually.
Entering a Python and then it should work.
So you said Python.
Hyphen n, hyphen n, pip install, and do write pandas, space pandas. Hyphen m for mango.
And pip install pandas. All right. Perfect. And then that should pull that up automatically. Good to go.
Usually what you can do is like keep a requirements.py file or txt file and keep on adding the libraries in that, and at the end you just need to run that txt file with the same command. So it will download all the libraries.
Gotcha. That makes sense. So just have a separate file.
This should take the pandas red thing.
Yeah, there we go. So we print the housing data, and you can see here now that we have longitude, latitude, median house value, ocean proximity, and then we have from 0 to 20,639. So we have 20,640 actual houses in the data set. So, all right, cool. That's simple enough right there. So we have the data set. When load housing data is called, it looks for the datasets housing TGZ file. If it does not find it, it creates a datasets directory, which it did. You can see it did that in my code editor here. So I have the data in my code editor now. Downloads the housing.tgz file from the Ageron/data GitHub repository and extracts its contents into the datasets directory. This creates the datasets housing directory with the housing.csv file inside of it. Lastly, the function loads this CSV file into a pandas data frame object containing all the data and returns it. So I'm not too positive exactly what the data frame object is, but I'm guessing it's a class in Python that makes working with certain type of data easier. Is anyone aware of exactly what the data frame is?
Yeah, so data frame is like rows and column format, like how you have like it's a typical table format.
Yep.
So that's what data frame is. It's kind of like a common term in like all data processing. Even in R they call it data frame.
Okay, cool. So it's just a table that makes working with data easier. Cool. All right, so take a look at the data structure. You start by looking at the top 5 rows of data using the data frame's head method. Top 5 rows of the data set in this image here. Each row represents one district. So 0, 1, 2, 3, 4, they all represent a different district. There are 10 attributes. They're not all shown in the screenshots. So we have longitude, latitude, housing, median age, total rooms, total bedrooms, population, households, median income, median house value, and ocean proximity. The info method is useful to get a quick description of the data, in particular the total number of rows, each attribute's type, and the number of non-null values. Okay, so it's going to show you how many of the homes actually have this attribute available. Let me go ahead and just print housing.head. That's what it said, I believe. Yeah, so same thing we had over here, just the top 5 basically, so you could get an idea what the set looks like. And then if we go ahead and do info, there we go. So you can see all the different features available. Info, it seems, is pretty good because the just housing data set and the head, they don't show you all the attributes. So if you want to see all the attributes, .info is going to be the one you want to use. In this book, when a code example contains a mix of code and outputs, as is the case here, it is formatted like the Python interpreter for better readability. The code lines are prefixed with arrows or dots, and the outputs have no prefix. So there are 20,640 instances in the data set, which means that it is fairly small by machine learning standards, but it's perfect to get started. You notice that total bedrooms attribute has only 20,433. Oh, yep. Yeah, so that one's short. So there's some houses that are actually missing this attribute. So you're missing data on that one, meaning that 207 districts are missing this feature. We'll have to take care of this later. Good to know. All attributes are numerical except the ocean proximity. Its type is object, so it could hold any kind of Python object. But since you loaded this data from a CSV file, you know that it must be a text attribute. When you looked at the top 5 rows, you probably noticed that the values in the ocean proximity column were repetitive, which means that it's probably a categorical attribute. Let's see. Oh, yeah. Near bay. Okay, so categorical. Some are I know a couple of them are like inland or near ocean, that sort of thing. Oh, yep. Here we go. You could find out what categories exist and how many districts belong to each category by using the value counts method. All right. So if I print our housing data set with ocean proximity dot value counts. There we go. All right, so if you want to get the like how many are categorized in certain attributes. All right, cool. So most of them are less than an hour from the ocean, then inland, near ocean, near bay, and only 5 of them are on an island. All right, cool. So value counts. Let's look at the other fields. The describe method shows a summary of the numerical attributes. So this is gonna leave out the categorical attributes. And it looks with this, it looks like we're getting a minimum, a maximum, so you could see the ranges, what percentage are around certain values, and then a total count and a mean count. So that's going to be print housing describe. Looks like this is giving us just more information than the previous methods. Cool. Does anyone have a better idea on the 25%, the 50%, the 70%? Exactly what that? So,
You ever seen those box plots that have the tails and then like the size of the rectangle in the middle?
yeah, yes.
That's what those quantities are equal to.
So, like, if you were to just read it, let me see if I got this right. The 25% of the rows are below that.
Okay. So with the median housing value, the minimum is going to be about 15,000, 14,999. The maximum is going to be 501,000, and then 25% of the properties are at least this. 50% of the properties are this, at least this, right? Or lower. Uh, 50%, the median would be 179, so the 50%. Okay, cool. Yeah, that makes sense. Does anyone have any questions on that? I know we're getting more into the
I'll make a
statistical.
comment.
Yeah, sure.
I like how we're going in compared to the last time we did this. It's kind of nice going in and doing it line by line. So I appreciate that.
I agree. I agree. Yeah, thank you for that.
We're not going to get through this whole chapter tonight.
No, and that's totally fine. We'll continue to talk about this chapter throughout the week to just make sure that we really have it. So next week when we finish up this chapter or continue moving through the chapter, it's just like everything is sticking, you know. 4 weeks from now, 8 weeks from now, we're still able to reference this chapter and talk about it, even if it's with people who are new, you know, who have never done any machine learning stuff. So, yeah.
I like how you're doing it in your own. Forget the IDE you're using.
PyCharm.
I like how you're doing PyCharm. I like that. Honestly, I think we should all do it.
I agree.
After during the week, and people have ideas on how to parameterize the URL and things like that. Do that, and then come back next week and show here's how you. That's fun. That's cool.
Yes, yes. Yeah, or share it in the machine learning chat.
Yeah.
Cool. So the count, mean, min, and max rows are self-explanatory. Yeah, that makes sense. Note that the null values are ignored. So for example, the count of total bedrooms is 20,433, not 20,640. The STD row shows the standard deviation, which means how dispersed the values are. The 25, does anyone have a better understanding of standard deviation, what this line means here? If not, we could have someone just do a quick Google search.
Yeah, it's like this. It's a measure of how typical it is a piece of data, of how much a piece of data might deviate from the mean to the.
Okay.
So like if you were to take all of the data and add it together and divide it by the number of data points, that would give you the average value of the data, right? You understand that? And then that's the mean, it's the average, right? The standard deviation is sort of like it would tell you it's the average difference between each data point and the mean. So it tells you that if you were to take a random piece of data, how much do you expect that it's different from the average value of all the data?
All right, so for example, with the median house value here, the mean is 206,855. Now, if we went through every single property in the data set and we checked how far each one is from the mean, so like one of them is going to be 20,000 away from the mean, the house value, another one's going to be 250,000 away, another one's going to be 80,000 away, and when you add up all those and divide by the number that you added up, you're about 115,000 away from the mean.
That sounds like a good. Now, one thing I was trying to think of a good way to say it. Somebody chime in if this is right. Imagine like a bell curve of prices or ranges. There's like if the bell curve was like a thin, then maybe that's a lower. If it's a wider, then that's a higher standard deviation. Maybe that's not the right way to say it, but I remember. I hear my echo. In the previous time we did this meeting, somebody got on and really got into this, and it was super helpful. And it's like they even like drew out a graph like here's so.
Justin, yeah, I remember.
You know what I'm talking about. Like,
yep.
Not just jumping over terms we've heard all our lives, deviation, but to get into it because maybe we're not to that section yet, but you know what I was talking about. Somebody got in and like they almost drew like a step diagram. I'll try to remember that as we get closer to where that'll be interesting. But okay.
Yeah. Yes. And that's part of the good thing about these meetings here. If you do already know the answer, like if you already do have information about like what is the standard deviation, definitely speak up and share that. It's going to, like teaching it to other people who don't know it yet is going to reinforce the stuff you do know, and it's going to help you learn how to articulate these complex topics to other people. And then for the newer people who are just learning what this stuff is, still give it a shot to articulate it. Like try to explain it to everybody else if you really want to learn it, because one, it's going to help you reinforce learning all this stuff. And then two, I think one of the toughest things for people is like, I meet people all the time who are just like top level coders who are just, man, they can solve a problem so fast, but when they actually have to articulate the solution or articulate these concepts, it's just, that's a skill in itself. So definitely if you want to try to articulate and explain this stuff, even if you're newer, feel free to just give it a shot, and the people with more experience or just a clearer explanation will definitely correct you or fine tune what you're saying. So the 25%, hey.
Hey, Jim. A minute ago, you explained it perfectly. The standard deviation is the shape parameter for
Awesome. Did someone else have something?
Yeah, I was just gonna. This is Rob. I was gonna be less scientific about it because I couldn't quite remember the numbers, but I did Google it. And right, if we think about the bell curve, and what's the middle of a bell curve, right? Each standard deviation tells us how far we move one way or the other, right? And so, one standard deviation from the midpoint will represent 68% of that bell curve. So basically, what is I don't have the numbers here. The number's 2, then you add 2 and subtract 2 from that, and 68% of these numbers are going to be within that range. So it's a way to think about it. If I remember, like 98% the distribution should be within 3 standard deviations of the midpoint, or the middle.
Yeah, and for those who are like, I still don't really get it, there's a couple people who posted in the chat here, Aditya and Sweeper. And yeah, we have a couple people posting more about the standard deviation here, so feel free to.
As a measure of squishiness is good, though. I feel like it's worth noting it's not necessarily specific to a Gaussian. Like it's a quantity you can have about any regular, right? Be all skewed to the X or something.
I think the best way is like the best way to plot this is like just draw a median line and then just plot the points. And then accordingly, you can understand that like for every variable, like how away it's from that median. Like the coordinate axis is draw at 0, or like some select median point, and then just plot the values, and you can see like I think box plot is one good thing to see, right? The standard deviation.
I haven't used that before. Awesome. Thank you. You're saying instead of just having one peak, like this one that Sweeper shared last, they could have like 2 peaks?
Yes.
Okay, gotcha. He said bimodal. I'm just making sure. Cool. Awesome. Thank you, everybody, for sharing. The 25%, 50, and 75% rows show the corresponding percentiles. A percentile indicates the value below which a given percentage of observations in a group of observations fall. For example, 25% of the districts have a housing median age lower than 18, while 50% are lower than 29 and 75% are lower than 37. Okay, so it's showing what's lower. These are often called the 25th percentile or first quartile, the median, and the 75th percentile or third quartile. Another quick way to get a feel of the type of data you're dealing with is to plot a histogram for each numerical attribute. A histogram shows the number of instances on the vertical axis that have a given value range. On the horizontal axis, you can either plot this one attribute at a time, or you can call the hist method on the whole data set as shown in the following code example, and it will plot a histogram for each numerical attribute. So I'm going to go ahead and type that out. Let me just go ahead and how do I start a new one here? All right, so to install matplot, it's python -m pip install, right?
Yeah, I mean, since you don't have pip, so you can basically use python -pip. But usually, like, if you have pip installed, then you can just use pip install. Pip is like a package manager.
Okay, gotcha. Yeah, if you already have Python. Yeah,
Like
gotcha.
npm, basically.
Yep. Cool. So let me go ahead and add this library here. Matplotlib.pyplot. So this is a library for actually plotting data with a graph. So housing.hist bins equals 50. Fig size 12.8, and then I will print. Actually, I don't think I have to print for this one. Plot.show. Let's see what we got here. All right, cool. So these are our histograms for the different data. The longitude is everywhere from -124 to -114. Latitude, you can see we're going from like the, I guess, low 30s to 42. Housing median age, a little over 0 to a little over 50. Total rooms, it looks like they're all concentrated in the lower numbers, probably like 2, 3, 4. Total bedrooms, same thing. Population, same thing. Households, same thing. It is just that right there. Thank you. So looking at these histograms, you notice a few things. First, the median income attribute does not look like it is expressed in US dollars. The median income right here, it's not expressed in US dollars because it's from 0 to 15. After checking with the team that collected the data, you're told that the data has been scaled and capped at 15, actually 15.0001 for higher median incomes, and at 0.5, actually 0.4999 for lower median incomes. The numbers represent roughly tens of thousands of dollars. 3 actually means about 30,000. Okay, so 5 means 50,000, 10 means 100,000. Working with pre-processed attributes is common in machine learning and is not necessarily a problem, but you should try to understand how the data was computed. Yeah, so at bare minimum, understanding the data. That's like one of the main steps. The housing median age and the median house value were also capped. So the housing median age looked like it was capped at 50. And the median house value, same thing. Yeah, it looks like it was capped as well. The latter may be a serious problem since it's your target attribute, your labels. Okay, so the house value is our labels, and so the fact that it's capped could be a problem. Your machine learning algorithms may learn that prices never go beyond that limit, even though in reality they do. So you kind of have to think through these problems practically too, like as you're looking at the data. And really, I feel like you really have to, when you're building your own machine learning projects, that you really have to just like think about each one of these independently and think like if the data is displayed, categorized, or just like presented in a way that makes sense practically, you know? It's interesting.
Well, you want to talk about why there's a cap? You know, is that a cap that you know we selected because beyond that the data follows a whole another set of rules, or because that's just how we got the data, you have to deal with it?
I'd say if they explain it in the book, we'll go ahead, but I don't want to like speculate.
Okay.
So you'll need to check with your client team, the team that will use your system's output, to see if this is a problem or not. If they tell you that they need precise predictions even beyond 500,000, then you have two options. Collect proper labels for the districts whose labels were capped. Ah, got you. So they were capped, but the true data does exist. So the actual values does exist. Maybe it exists, maybe it doesn't. I don't want to make any assumptions. Remove those districts from the training set and also from the test set, since your system should not be evaluated poorly if it predicts values beyond $500,000. Huh, okay. That makes sense too. These attributes have very different scales. We will discuss this later in this chapter when we explore feature scaling. Finally, many histograms are skewed right. They extend much farther to the right of the median than to the left. This may make it a bit harder for some machine learning algorithms to detect patterns. Later, you'll try transforming these attributes to have more symmetrical and bell-shaped distribution. So we're actually looking for a balanced and bell-shaped distribution. If they look like they're too skewed one way or the other, we want to apply tactics to balance them out. That's what it sounds like, but does anyone else have any thoughts or want to share anything on that?
As far as what I know, usually the data sets like should be like, I think they call it like kind of like uniformly distributed something. So like if it's like skewed completely, I think they kind of perform some kind of oversampling or undersampling transformations, something like that. But I'm always like unsure like how exactly you can kind of like interpolate or extrapolate data, like based on, because either you need to collect more data, but like how exactly you do that. So because that also kind of you need to discuss with your client to ask him like, do you really need to like
Mm-hmm.
With summary is extrapolating star. For low-dimensional data, it's pretty straightforward.
But like considering like the domain, like this domain is kind of like the realistic domain, right? So like do you like does it like recommend it to do kind of like interpolating or extrapolating it, like data, like making it like uniform just by using operations, or like better to like collect more data? How exactly? Like I'm always like in that doubt. Like it's better to like ask your client or like discuss, brainstorm. Like do we really need to do that? Because that like might like bring some false positives as well, right? Like false negatives.
Those are good questions. Thank you. Awesome. Thanks, everybody. All right. So before we look at the data any further, we need to create a test set, put it aside, and never look at it. So we're going to start creating a test set. It may seem strange to voluntarily set aside part of the data at this stage. After all, you have only taken a quick glance at the data, and surely you should learn a whole lot about it before you decide what algorithms to use, right? This is true, but your brain is an amazing pattern detection system, which also means that it's highly prone to overfitting. If you look at the test set, you may stumble upon some seemingly interesting pattern in the test data that leads you to select a particular kind of machine learning model. When you estimate the generalization error using the test set, your estimate will be too optimistic, and you'll launch a system that will not perform as well as expected. This is called data snooping biased. So, yeah, okay, that's interesting. I'm just going to, I want to look into that a little more. Not right now, but just for later. Feel free, if anyone else is interested in that, to go ahead and go down a rabbit hole if you would like. I'm just gonna dig into it a little bit later. I'll share what I find in the machine learning channel. Creating a test set is theoretically simple. Pick some instances randomly, typically 20% of the data set or less if your data set is very large, and set them aside. So, all right, we're gonna create a function called shuffle and split data. So we're going to be passing in the data. We're going to be passing in a test ratio as the argument. And then it looks like we're going to be calling this function with our housing data set. And 0.2 is going to give us 20% of the data set. Okay, so we're returning the training indices and the test indices. All right, so we have our test ratio. Okay. Cool. I'm going to go ahead and type this out. Feel free to run this code in your Jupyter notebook. And for those who are not typing the code themselves or running it in their Jupyter notebook, feel free to go down rabbit holes, do a little Google search if there's anything here you don't understand as far as training or test set related. Or if you're not doing either and you just want to share a little bit of information about training and test sets, feel free to do that as well. I'm just going to take a minute to type this out. Yeah, so I believe, correct me if I'm wrong, but I believe this shuffle and split data function. All right, so if we just walk through it, NP random permutation. I believe this is going to shuffle the data and just give us a random permutation, so mix it up in a way that is unpredictable. Yeah, because it returns shuffled indices, and then we're going to create a test set size, and we're going to use the test ratio to do that. So the 0.2 that we're passing in times the length of the data is going to, and convert it into an integer. That's going to give us 20% of the test size, test set size. So this is going to give us the actual size of our test set. And then we have our shuffled indices and our shuffled indices. In this one, we're going to take test set size. This is going to give us, since the colon is in the front and the test set size is after, I believe this is going to be 80% of our data stored as the test indices. And then, or this is going to be 20% of our data stored as the test indices. And then since the colon is after, this is going to be 80% of our data as the training indices. So we're going to use 80% of our data set to actually train the model. And we're going to use 20% of the data set to test our model. And then we're going to return our training indices and our testing indices. So we're basically taking the data, we're splitting it 80-20. We're using the 80% as our training to train the model. And then we're using 20% of the data to test the model that we've trained to basically check its accuracy. Definitely correct.
Training itself requires a lot of data too.
Yeah.
Actually, we learned about this a bit, like in some of my courses. Guys, something you guys can look into later is the term is information theory, but it's pretty relevant. A big reason why we separate them is because you're supposed to think of them as being independent, even though they came from the same data set, right? So the reason we even make the split in the first place versus just training it with all the data and then testing it with data is because when we train our model gains information from the data that was trained. So if we train it using the same data, if we test it using the same data we trained it on, it's going to perform on it better than it should. Right? The point of the classifier or the regression is to see how well it can predict and stuff like that.
Right. Are you saying
I
like,
got what you were asking there.
are you saying something like taking a subset and then inferring and generalizing the whole population of the data? Right. Right.
So it is a known problem for splitting the test and train into 80-20 split, and which is why further in the chapter I guess you would learn about 5-fold cross validation or 10-fold cross validation, where this 80-20. So imagine a data which is now split into 5 parts. 4 parts are used for training. The then we can change those code paths, go for another set of code. So we keep shuffling those code paths before filling the test. So that kind of solves that problem. Yes. So the way currently they are splitting the data, we will have the problem that you're saying. But if further we keep suffering like this, 80% data is suffered. Now you bring in the test data into train, you take some of the train data into test, you shuffle, and you shuffle let's say 10 times or 5 times. That takes care of your difficult problem.
Yeah, that makes sense. So if you shuffle the data 5 times, then or let's just say you're shuffling the data, you're using this function 100 times. By the 100th time, the training it's been trained on all the data.
Say this again.
I'm saying if you execute this shuffle and split data function like dozens or hundreds of times, however many times over the course of however long you're running this project, eventually your model is trained on all the data, right?
You think of it as if each split is independent, right? What you're converging on as you do more cross-validation iterations is the expected competency of your model,
Mm-hmm.
right? So it's not the case that you're training the same model on multiple cross-validations.
So, well, one of the interesting things that, as you see in this beginnings of the books, is explanation of, why don't you take all the data and train all the data, and because then you're just training to that data. So, just in case anybody didn't get that, so you have to have that data to the side to test against and not train on, because it has to deal with the data that it doesn't see, which someone already said. But I thought that was a very interesting point. But if what I didn't get, some people were saying, the shuffling of the data here to create, one bucket of 80% and another 20. I mean, you can do that over and over again and run the. To me, you're going to end up with a new model based on each different 80% of the data. Now, how you have a different model for each time you run it. I'm not sure how you sort of integrate those into one overall model.
You're right. You're right about that. That you will take different models from different splitting, but you would try to change your parameters of set of parameters such that you get very close predictions from each of the splitting models. So let's say if you take 5 splittings, like 5 iteration of splitting into 80 and 20, and you have 5 models. All 5 models, if they are performing really close to each other, then you can pick the best of them, or you can do it.
What is a hyperparameter again? I'm sorry.
Hyperparameter, for example, anything that you can change during model building, like for example, if you're using a certain kind of model input, you can change the number of layers that you're using, number of nodes that you're using. So those are the hyperparameters that you will change it during the fitting of the data.
Okay, thank you.
Awesome, thank you.
Because that is the case in the would be more like you choosing the quadratic equation versus like a linear equation, right? It's like the curves and you're fitting, like something to help me understand it better was like it's often not the case that your final model is is trained on a cross-validated scheme, right? So it might be the case I have some data and I want to see if a linear regression fits with better in general or a quadratic regression fits with better in general. So I might do 5 cross-validation splits. And I'm going to train 5 linear models and 5 quadratic models and see how well they perform on each split. Maybe I'll take an average, right? And maybe I see on average the linear model tends to get have an R squared of like 0.98 versus the quadratic one tends to have 0.9. So I say, okay, that is a bit better. Then when I want to deploy my model, I train it on all of the data. Right? So it's a bit of a heuristic sort of to tell you about if your design choices are better on the data in general.
That makes sense. So basically, what you choose from the hyperparameters affect the architecture of your neural network. Correct?
The meaning of hyperparameter will become clear as we come on. It's like the inputs too. So it'll become clear.
Yeah, I believe we go into some hyperparameter stuff during this project as well. So yeah. So I went ahead and I ran this. I created the function here. Like I said, we're splitting it into a training set of 80% of the data set and a test of 20% of the data set. And then when I ran it, you can see we have a training set length of 16,512, a test set of 4,128. So this works, but it's not perfect. If you run the program again, it will generate a different test set. Over time, you or your machine learning algorithms will get to see the whole data set, which is what you want to avoid. That's basically what I was saying. One solution is to save the test set on the first run and then load it in subsequent runs. Another option is to set the random number generator seed with NP random seed 42 before calling NP random permutation so that it always generates the same shuffled indices. Okay. However, both these solutions will break the next time you fetch an updated data set. To have a stable train test split, even after updating the data set, a common solution is to use each instance's identifier to decide whether or not it should go in the test set, assuming instances have unique and immutable identifiers. Alright, so it's important that the training set and the test set remain consistent over time. For example, you could compute a hash of each instance's identifier and put that instance in the test set. If the hash is lower than or equal to 20% of the maximum hash value, this ensures that the test set will remain consistent across multiple runs, even if you refresh the data set. The new test set will contain 20% of the new instances, but it will not contain any instance that was previously in the training set. So we'll keep our training set, and our test set, our test set, regardless of how many times we run this function. Well, this shuffle and split function sounds like it's not the one that we want to use. So I'm going to go ahead and just comment that out because it looks like we're going to be building a different way of doing this. So from zlib import crc32, and then we have two functions, is ID and test set. So we're checking if the ID exists in the test set with this calculation here, and then we're splitting data with ID hash. So we're passing in the data, we're passing in the test ratio, and we're passing in the ID column. Sounds like we're adding an ID column to our data set, and then we're using that to break our data into a training set and a test set. That's what it sounds like. Let me know if I'm wrong, though. Does someone want to go ahead and continue reading from right here for the next couple paragraphs?
Sure, I can read.
Yeah, do your thing.
So unfortunately, the housing data set does not have an identifier column. The simplest solution is to use the row index as the ID. We have housing with ID, so we assign that. Then we assign two variables. We split by the ID. So if you use the row index as a unique identifier, you need to make sure that new data gets appended to the end of the data set, and that no row ever gets deleted. If this is not possible, then you can try to use the most stable features of node identifier. For example, districts latitude and longitude are guaranteed to be stable for a few million years, so you can combine them into an ID mix.
So why do we need an ID?
It's basically to make the data set consistent.
We are not updating or deleting the data sets, so we're using the same data set.
You want to keep the same data in the training section and the sort of the same in the test section, even if you get like a whole updated file with that has now has 100,000 more rows. Setting up a system where it splits it again, and you're not sort of mixing up the training data and the test data, because you don't want to train the model on the test data. The test data has to be independent to be a valid test. If it's trained on the test data, then the test isn't telling you anything. So the system where you're making you're splitting, is ready to deal with, inputted new data. That makes sense. And to get a unique. Go ahead.
So the split happens on the ID column, using the ID column.
Yeah, you want a column that the data doesn't change to base your function on that is going to split, decide, well, this row goes in this bucket or it goes in this other bucket. So if it's a field that won't change, it'll always put it in the right spot. And it'll even okay. I think we shouldn't think about that. I think for now we can keep it straightforward.
Yes.
Yeah. We'll get to more complicated versions of it. But for right now, it's good to say, here's the training, here's the test, and you don't mix them. Yeah, the ID field that we're creating, because there isn't one, or you can create out of latitude, is getting something that won't change, that you can run this hash formula on to divide them into buckets, and you'll know that it will always put them in the, if you did it on price, that would change, then you have data that would jump from bucket to bucket, but when you have a field that won't ever change, you'll know that your data is going in the right spot.
Yeah, so it sounds like with our previous method, we're shuffling and splitting the data. So if you run this function over and over, then eventually all data is going to end up in the training set and the test set, and both our model is going to know everything, all the data. It will have processed all of our data. With this method here, it looks like when we're creating housing with ID, we're adding an index column. Oops. We're adding an index column to each, basically like each property within our data set. So for every single house listing in our data set, we're going to add an index to it. We're going to add the index column. Then to create our training and our test set, it looks like we're passing in our data set to the train test split. So this new function here, split data with ID and hash. Oh wait, I went too far down. Split data with ID and hash. We're passing in the housing with ID. So this is our housing data with the index column added to it. And we still want 20%. So we want our test set to be 20%. And the column that we want to use to figure out whether we add it to the test set or the training set is the ID column, which is our housing with ID, so our index. So when you look at this function, split data with ID hash, we're passing in the housing data with ID 0.2 and the ID column. And then inside this function, for each ID column, we're creating an array of IDs, I believe. And then we're determining whether each is going to be in the test set or in the training set. And so I don't exactly know what a lambda function is, but we're using the ID. So for every ID, so for every listing in our data set, we're running is ID in test set. So we're using that ID and the test ratio 0.2 to use the identifier. So if the identifier, let's just say for every element in our data is like 0, 1, 2, 3, 4, 5, 6, 7, 8, you know, this one will be 2, the next one will be 3, the next one will be 4, the next one will be 5 or whatever. And we're converting it into a 64-bit integer. And if that result is less than the test ratio times 2 to the power of 32, then it's in our test set. If it's not greater than, then it's in our training set. So regardless of whether the data set changes or like more data is added to it, regardless, the IDs or the index that we added to it is going to be the same. And since the index is going to be the same, if the first property in the data set has a certain ID, it's always going to have that ID. It's either always going to be in the test set or it's always going to be in the training set based on these functions right here. I might have explained it good. I don't know. I definitely it makes sense.
That's pretty good.
Can you show what's next to the 0.2? Another one.
This one here.
One above.
This one here.
Thank you.
So split data with ID hash. We're passing in the housing data with the ID. We're using this is our test ratio, and this is the index column that we're using to determine whether it belongs in the test set or the training set. And then based on this column that we just added to our training set, we determine whether it's in the test set or the training set. And yeah, it's either always going to be in the test set or always going to be in the training set. You're never going to mix and match the two. So I could see how that solves the problem that we encountered with the first function.
You know, it's going through steps of difference. So, like the step where it says, here's re-adding the index column, it's like, well, that's a little bit better. But then, you know, when you get new data, you have to make sure it's appended to the bottom of the, to the, added after the data you already got. And sometimes that may not be so easy. Like you may get another new file, and whoever's giving it to you, you know, they're giving it to you. You added the index on that. Maybe they're giving it to you in a different order, and you're left with thinking, well, you know, now I have to figure out what the, you know, get them. So the last says, okay, now we're creating an ID that is non-dependent on the index of the file is sort of is even better. Does that make sense?
Yeah, I'm pretty sure that's what we're doing next. Yeah, if you look down here, we're actually.
The next one down.
Guys, I got a question though. I'm probably missing something, but I get what we're doing here. But then doesn't this start to reduce the randomness about what goes into test and what goes into training? Right? If we're using a piece of data to create this index, then we're kind of beginning to sort, right, specific pieces of our data. More data is going to show in test and not in training. Isn't that what's going to be happening here? Does that make sense?
Like if you got a whole new bucket of data, still going to split it by 20%.
No,
so
right. But like to use this example, like it's using latitude and longitude and saying, okay, when we do this calculation on longitude and latitude, if it's below a certain value, it's going into test.
Yes. Yeah. If you use latitude or longitude to split it into a training set and a test set, then yes, you would be sorting it based on an attribute that already exists in the data. But since we're adding a new column, since we're adding an index column that is totally random and has nothing to do with any of the other attributes in the data, then it's totally random split. It has nothing to do.
Okay.
Yeah.
Okay. I thought that index was based on the longitude. I can't really see.
let me.
As an alternative example, the reason they added it together is just for 1 by 5,000 to try and mitigate what you're saying. They essentially have a hash.
Okay.
Yep.
Okay, I got it. Okay, so that munging of it in a sense creates
So
Yes.
it's creating the number that should be pretty unique based on the latitude and longitude, but it's not sorting them by the latitude and longitude. Then it's multiplying a hash, which then creates a number that will not group up. Here's half of the state is on one side of it, and the other half of the state is on the other side.
Yeah, I got it. I sorry, I couldn't. Thanks.
I have a question. So it's like when do you hear me?
Yes.
So like in like real world, the way training works is like, for example, like you have, let's say, data for like 10 years, let's say 2010 to 2020, and you have that data and you train a model. Now when let's say the data gets updated or like new data you want to append, it's not like you already have a trained model. Like is it like more feasible like to like use that previous data, append new data, again train the model, or would it be like use the trained model and like again train the model with the new data and like use that model which is trained and kind of like it's like you save the model, right? You basically use that model and just train it with the new data rather than like appending and again training with that entire data. Like that's why like I don't know like if this append thing like works in real world, like unless like you get that data before you have trained something like the new data. But like if you've already trained the model and let's say if the new data comes, like how ChatGPT works, like I don't think they're like going to like let's say have trained the model till like 2020, and now like if the new data comes, I don't think they will train the model again with the start of the data with the new data. They'll basically use that model and kind of append like learn that same model with the new data.
Update it. Yeah, that makes sense. Yeah, well, it's 7:37 right now, so I'm gonna be hopping off. Feel free to stay in here and hang out, chat as long as you would like. We'll be meeting back here again next Wednesday at 6 p.m. Eastern Standard Time, and we'll continue where we left off. But keep the chat going in the machine learning channel down here. Feel free to continue working through the book. I'm going to continue working through the book as well. But yeah, we'll leave off.
Are you leaving? Can you keep this chat still talking?
Yeah. I'm just gonna hop off all of you guys. Yeah, whoever wants to stay and just chat about random, news or machine learning or whatever you want to do, feel free to hang out as long as you want.
I wanted to tackle the challenge of trying to explain a lambda, which is a fun thing to try to explain. And I'm sure some of you already know it, but some of you don't. A lambda is an anonymous function, so it's like